All right. So my name is Raymond. As thank you, Adam, for inviting me to this event. Very grateful. Today, I'd like to talk a bit about my journey from being an engineer, stepping into the startup world, and then eventually I'm doing a bit of angel investing um, uh, for the past few years. So, when you see my title, it's kind of long and windy, and frankly, I have to admit, I asked ChatGPT to generate a title for me. I told it to, hey, I want to talk about a bit about my industry, which is semiconductor, deep tech, and then I'm also an entrepreneur, started a few companies, and I'm investing too. So that's what it's been. And for what it's worth, this three different areas, and I'm gonna be talking a bit about. So, where's my control? There we go. Who am I? You know my name. My name is Raymond. Um, I've told you I'm an engineer, I'm an entrepreneur, and also an angel investor. But going back to my roots, this is where I started my engineering career. I was trained as a chip design engineer from University of Toronto Engineering. I got my PhD there in the mid 90s. I also got my iron ring. If anybody doesn't know what this is a ring that if you are graduated from a Canadian engineering university, then you are given such a ring called iron ring. And this purpose is to remind you that you need to be ethical, you need to be moral, you need to be a good engineer, all that good stuff. So I have been wearing this for 35 years. So for the past 35 years, this is what I do. Chip design, 3 decades of chip design engineering. The black and white photo there is one of the circuit designs that I did during my PhD. This has about, I don't want to go into details, but this has about 200 or 300 transistors in there. And from the in the right hand side, the colorful pictures, which brings us to today. It's a modern day wafer that consists of a lot of different circuit dies, if you will, chips. Each little square, by the looks of it, I don't know exactly, it's probably has a billion transistor or more in there. So you can see three decades of evolution and engineering that brings us to nowadays. So when I finished my PhD, I was basically a nerd, techie. Went into corporate world of design a few chips there in the corporate environment. Was pretty happy about it because I got to use my skill that I learned from school to make products. But somewhere along the line, which was about 20 years ago, I took the plunge into the startup world and helped started my first startup company, being a founding member, founded by two professors at U of T, called Snowbush Microelectronics. That was a completely bootstrapped business, more on the design service side. Was there about 7 or 8 years. Luckily, got an exit through acquisition, and then moved on to my next startup, which is Envisage, again founded by a university professor, which I joined really early on. Long story short, it also got an exit bought by Apple, a very small exit, but still an exit, which led me to 2008, when I co-founded Capic Integration with another professor from U of T. So my career has so far at this point still very attached with U of T because all my startups have been associated with very closely associated with U of T. So the Capic also was by the way, Invigis was a VC funded business, and Capic now, 2008, back to bootstrapping. So we bootstrapped at Capic as a design services firm, doing chip designs for other companies for about 10 years. And along the way, we actually tried to do different spin-offs. And that's really the model of Capic integration. You do a bootstrapped business, which in that kind of bootstrapped business, which is services, you don't get your hockey stick effect because we're not building products. We are offering services, so we get services fees and whatnot. So, but that keeps us alive and well and profitable. But we didn't want to develop products within the Capic integration platform, because once we knew we did that, especially in semiconductor and hardware, it's very capital intensive. You need a lot of venture capital money to get a product out the door. So we didn't want to make a big bet on the particular product within the Capic platform, because once you get money, it's either going to be very successful, or chances are there's a bigger chance that it will fail, that will pull the company down. So what we decided to do is through the design services platform, we look at a lot of different market verticals. For example, in our business, electronics, sensor technologies, data communication technologies, and RF technologies, all that kind of different verticals, we actually can provide services. And while you work with a real customer in a real problem, you develop IPs, you develop techniques, you develop technologies, understands what the market requirements are. That allows us to think about what kind of product we'd like to build. There are a few attempts, but at the end, we sort of found something that seemed useful and interested by investors, which led us to the spin-off of Untether-ai, which is where I'm currently at too. By the way, Capic's still going on. So what we did, what's Untether-ai? Obviously, with the name, it has to do with AI. It actually is a AI chip company. So we developed and incubated the ideas and initial product ideas and a business plan or business case within Capic, and also tried to look for our seed capital when we're still at Capic. Once we landed us, we spin it off. That was 2000. That was 6 years ago. And I neglected to add another sort of a sidetrack to Capic, because Capic also had spun off another company called Star-IC, which I am not operationally involved in, but Capic owns part of it. So what happens from a corporate structure perspective is Capic owns part of Untether-ai, and also Capic owns part of this Star-IC, which doesn't exist in this slide. I neglected to put on. But I have been spending most of my time anyways with Untether-ai for the past number of years. And currently different capacities as a co-founder, but currently mostly I'm serving as chair of the board there. So that's kind of my startup journey up till now. And I think I'm a serial entrepreneur, so I think I will be doing something new again down the road. But that's where I'm at from a starting a startup perspective. In recent years, in the past 3 or 4 years, I've ventured also into angel investing, mentorship, advising companies, and volunteering, all kinds of different activities I'm going in my spare time. So I've, at this point in my career, I'm interested more so in helping the startup ecosystem, contributing back in form of angel investing, helping seed stage or seed stage companies, mentoring younger aspiring entrepreneurs, advising tech companies, and so on and so forth. So that's basically who I am. And since I am primarily a semiconductor guy, an engineer, so I tend to be a bit more technical, and I am very technical. So I'd like to actually share a bit of what shows actually how the semi evolved from the born of the transistor to where we are at now. If you allow me, if you allow me to sort of run you through that kind of evolution over the past many decades. So what I'm showing here is a picture of the world's first transistor demonstrated at Bell Labs. Glorified, it's a picture from the museum, but this is kind of what it was at 1947, December 23rd. That was the first demonstrated transistor. That was 75 years ago, 76 or 70 odd years ago. And fast forward 7 decades later, that's where we're at now. Everybody knows Apple. They've recently, a couple months ago, they announced their M3 chip that goes into the latest and greatest laptops, MacBooks. And what you can see here in the rightmost little squarey picture, that's what a chip, or we call it a die, looks like. That's inside M3 Max. This little die, believe it or not, contains 92 billion transistors. If you look at the left-hand side, that was one transistor. And now, in the size of that M3 Max is about the same size as the one below from NVIDIA, H100. It's around the same size, 800 millimeters square. And then the NVIDIA chip, which is the latest AI accelerator chip, H100, which is very expensive. Can't make it up a bit. It consists of 80 billion transistors. So that shows the progress of semiconductor technology from the 50s to where we're at now. Huge progress. So a very overview of the timeline. I'm just going to quickly go through that. It says sorry, my timer is doing something funny. Okay, anyways, sorry. 1950s, as I mentioned, invention of transistor. I call it 1950s, even though it's 1947. And 1960s is where we have what we call integrated circuits, IC chips, and where they put multiple transistors onto the same chip. The picture showing here is what we call a NOR gate. You don't have to understand what that is, but that has 4 transistors. So people are starting to put more transistors on the single chip. And then comes in the 70s, then comes the microprocessor, and memory chips is kind of what you're more used to nowadays, which led to the advent of personal computers, because you got these microprocessor chips. People started building personal computers, and then moving on to the internet and mobile communications era, more integration, smaller chips, and all that stuff. Multi-core processors. You're familiar with Intel's i-Core 7 with 4 cores, 8 cores, and when you buy your PC, basically putting more computers in the same chip. And interesting is in the recent 10 to 20 years, the advent of AI is coming. So AI is all about right now. And there's a reason behind that. It has to do with the semiconductor, because AI has been there for 30, 40 years. So it has always been there, but it's only the last 10, 15 years or so that is seeing its explosion. And that has to do with semiconductor. And of course, there's this IoT, Internet of Things, that's also happening, which is the edge computing, your smart watches, your smart wearables, headphones, earphones, which is smart, and which requires a very low power type of chips to power those applications. And then nowadays, everybody's talking about advanced AI chips. You can see NVIDIA is doing crazily well in terms of their sales and stock. That's really because of the need for AI. And the reason why I said semiconductor is behind the explosion of AI is because like 10, 15 years ago, AI researchers starting to see that there's the computing power of based on these semiconductor chips is finally enough to be able to run their complicated and large neural network models, AI models, to be able to do something meaningful. And that also fueled the currently we're living in a stage where everybody wants the most compute power to run their ChatGPT models, the LLM, large language models. There's also this quantum computing things going on. I'm not going to explain that at all because that's too complicated for me. That's a fancy high-level science. But you can always look at YouTube's. There's lots of YouTube tutorials out there. That's what it's about. But it's kind of still at its infancy stage. So it'll be interesting to see what happens there. So speaking of AI, I'm not going to go through these slides too much. I'm just wanting to say that Semiconductor is indeed powering AI computations. People started up using CPUs, which is not a great platform for AI compute because of various reasons. But I'm going to say that the way the CPU is built in such a way that data movement between the compute unit and the memory unit itself, because you're shipping data back and forth between these two, which is a classical computer architecture, burns most of the energy. And to solve that sort of problem, to minimize the energy burn by moving the data back and forth between these two components, the memory component and the CPU component, people started creating different architectures, such as GPU, which is graphics processor. Not so much for AI applications, but more for gaming applications originally, like 20 years ago. A lot of pixels in the game you have to process in parallel. So that's really what GPUs are good for, designed for. It's parallel processing, a lot of computations done together, much like you have to process the millions and millions of pixels per screen together at the same time, as much as possible. So that kind of a concept leads to the fact that the AI researchers realized that this type of GPU actually quite suitable for running AI workloads, because AI workloads, in some way, it's similar to processing video for games and processing many pixels together. Because in an AI algorithm, you've got a lot of simple math that you have to compute at the same time, in parallel, all together, which is not so efficient if you do it in the CPU, which doesn't lend itself to do that. So that's the reason why so successful, because they just caught onto this wave of AI, and that fueled also in turn, as the semiconductor, as NVIDIA put out better and better GPU chips, the capabilities of compute capabilities for AI researchers to rely on gets better and better, and that feeds into a loop, saying I've got better hardware, then I can do a better AI or more complicated AI model, which leads to the large language models now, like exploding now in GPT. And I think I think I've got a few more slides, quite a few more slides to go, but I think I'm out of time now. So I'm going to wrap up a little quickly. And
take your time, Raymond. Yeah, happy for you to continue, but also if you want to wrap it up, mate, yeah, up to you.
Yeah, I'll sort of accelerate a little bit because I'm getting too excited when I talk about technical stuff. So what's beyond GPU, meaning that GPU is kind of the king now, and NVIDIA is taking 90% of the market. OpenAI and all these large AI models relies on data centers that has tons and tons of GPUs in there, like 1,000, 10,000, 100,000 of GPUs in there. That's what the current situation. Because the market is so hot about building data centers and making hardwares for running AI workloads, there's got to be someone who's thinking about on GPU. After all, GPU wasn't originally built for running AI. It just so happens that it fits much better to run AI workloads than the classical CPU. And indeed, there are a lot of activities going on about people developing new class and new generations of what we call AI accelerator chips, which is specifically tailored for running AI workloads. I'm not going to bore you with these jargons, but the few different bullet points that I'm listing out here basically shows that there are multiple new ideas of compute architectures that is coming up online, and a lot of startups are doing these kind of stuff. I would say big companies are also doing it. For example, the neuromorphic compute, big on it. So they've done a couple of generations of chips based on this type of new architecture. It's really kind of brain inspired. It's kind of that with a neural word, you kind of get that. So this is a bit of a marketing spiel at Untether-ai. We are branding ourselves as at memory compute business. I'll just say one little point about it is the compute memory at memory. The idea is to bring the memory block into the compute block as close to each other as possible. The idea is to minimize the data traffic between the memory block and the compute blocks. So won't get into too much detail, but at Untether-ai, we feel that this type of approach at memory compute is the sweet spot for AI acceleration from a compute efficiency perspective. So moving a bit onto this start back to the AI startup topic, like starting a business, and if you are AI a startup founder, whether you're hardware or software, I would say one thing you need to work on is compute energy efficiency. I alluded to that before. That's because so many AI workloads coming online. There's lots of studies out there that try to predict how much electricity is required to power all these AI workloads and applications. For example, there are studies out there that predicts by the end of the decade, there could be single-digit percentage up to 15% points that is being used by AI workloads compared to worldwide electricity. So 15%, that's a very significant amount. And to put things in better perspective, so that you can maybe understand a little bit more about the energy usage, if you go into ChatGPT using DALL-E and whatnot, and ask it to generate an image, prompt it, and generate a dog wagging its tail, chasing after a cat or something, or the other way around. That actually is equivalent. The energy is required to do that. It's roughly equivalent to a full charge of a smartphone. So that's pretty significant. Think about it. And which leads to the ESG concern. When I say ESG, I think I'm mostly referring to the carbon emission, environmental. So that's an issue that is the industry is quite aware of, and a lot of startups and new architectures are actually in the AI chip space are actually attacking this energy efficiency problem. And Untether-ai is one of those companies. So regarding raising money for a hardware or semiconductor startup, it's not easy because most people or investors are not so comfortable about hardware. A lot more comfortable about investing in software. SaaS models, very, very popular. A few reasons behind it, because obviously building a hardware, especially if you're building a semiconductor company, it's lots of money. That chip that I showed you before here, our chip, that was our latest chip, doing it one shot cost us $10 million. So to TSMC, if you know what TSMC is, but needless to say, very capital intensive, especially in semiconductor. Obviously, you're looking for a longer term horizon. It usually takes a year or two to complete the full chip design. And also, hardware usually takes longer to fix or patch. The cycle time is longer. Unlike software, you can actually put patches out a little quicker. So those are kind of the perceived risk and difficulty for investors invest in hardware. But wait, dig a little bit more into the real numbers and statistics. You'll notice that more than 50% of the world's most valuable companies in the world are hardware companies. I think I'm talking about tech companies. So the hardware companies are not less valuable. In fact, it's probably more valuable than a software company. So the return is high, can be high, is what I'm saying. And also, like they actually are. All I'm saying is hardware and software companies, they both would lead to similar return multiples for investors. And what's more about hardware companies? I guess I'm sounding like a salesman for a hardware company, but anyways, that's my narrative. Typically, hardware startup has a stronger moat because you need a lot deeper technology to develop your semiconductor chip, and typically it's also harder for a copycat to do what you're doing. Now, I'm not saying it's not much harder. So you have a stronger moat typically. And from investors' perspective, if you're starting from the investor side, it actually is less competitive to invest in to find a startup to invest in. Here I'm showing a few. What I mean is, I'll explain what I mean here. I'm showing a few numbers here, the hardware, AI, SaaS, and fintech, and these are investor to startup ratios that I gathered these numbers from the link that I posted below. And when you see hardware investor to startup ratio is 0.3, that means every 3 investors, you've got 10 startups. So 3 investors will look at 10 startups. So that means startups would be hungry for your money. On the other spectrum, fintech in the fintech case, every 5 investor, you're dealing with 1 startup. So in fighting to put money into that particular startup. So that's how you interpret that. So if you look at it that way, investing in a hardware company actually is a good deal for an investor. And if you're an AI startup now, that's the biggest buzzword going around, and it's attracting a lot of capital. Global funding in 2023 in AI startups is about $50 billion. That's a lot of money. And pretty much the AI, pretty much if you're an AI company, you still get good deals, even though 2022, 2023 were really bad in terms of when you go out to raise capital. It was pretty dismal. And a lot of those money actually went into foundation model companies like OpenAI and Anthropic that develops AI models. But we're also seeing hardware semiconductor companies seeing increase in investment in these areas. I think people are realizing that the semiconductor or hardware is a pretty critical component for the future of AI development and all things too. I think angel investing that I'm doing, that's one of the things. Because, number one, it's fun. I like doing that kind of stuff because I get to learn new businesses, talk with different founders and learn their ideas and whatnot. And also at my stage of my career, I actually am very interested, more interested in helping the startup ecosystem, nurturing the startup ecosystem, especially in the hard tech, deep tech space, which is where my background is. Share experiences with young founders, and also if the companies that I deal with have very experienced founders, that's even better because I can learn from them. So it's a sharing and learning experience that I'm going after. And at the same time, I'm passionate about entrepreneurship, so I like to promote entrepreneurship. So I also do sort of community and ecosystem work, volunteering in business associations, mentoring at universities, and act as advisory roles to global technology startup companies. And that is it. Thank you.